Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Welcome, everybody. I'd like to welcome Dr. Jeffrey Hall to this Microsoft Research Talk series. Since June of 2010, Dr. Jeffrey Hall has served as the director of the Lowell Observatory in Flagstaff, Arizona, where Pluto, the dwarf planet, was discovered. He joined the staff of Lowell in 1992 as a postdoc research fellow and received his BA in physics in 1986 from Johns Hopkins University and a PhD in astronomy and astrophysics in 1991 from Penn State. His research at Lowell has focused on solar and stellar activity cycles with the goal of lending an astronomical perspective to solar influences on terrestrial climate. He presently serves as a member of the Northern Arizona Leadership Alliance and is a former president of the governing board of Northland Preparatory Academy, a college prep high school, as well as board of directors of the Flagstaff Symphony Orchestra. His principal avocation is music, and he's been a substitute organist in the Episcopal Church of Epiphany in Flagstaff for nearly 23 years. So please give a welcome to Dr. Jeffrey Hall.
Thank you. All right, well, thanks a lot. It's really a pleasure to be here with you today. I'm visiting the Seattle area from Flagstaff, a place where I've really enjoyed living the past 23 years, along with our staff member, Lisa Actor from Lowell. We are a private, nonprofit research institution. We have a number of supporters and friends, members of our advisory board here in the Seattle area. So we're just in the area for a couple of days making some visits, and we got to know Curtis Wong here at MS Research through conversations about the Worldwide Telescope, and when he heard we were coming up here, he said, well, would you like to come give a talk over at Microsoft? It's like, I would love to go give a talk at Microsoft. So here we are. Lowell Observatory is first and foremost a research institution. We were founded in 1894 by Percival Lowell. He was interested in observing what he thought was evidence of intelligent life, the famous canals on Mars. And since our earliest beginnings, we've grown to an institution that operates a campus on Mars Hill, just west of Flagstaff. And our research facilities have moved off-site to two separate dark sky sites. And most recently, we've opened a brand new 4-meter telescope that cost us a cool $53 million. And I'll come back to what we can do with that right at the very end. So these days, as the director of the observatory, I spend a little more time, it seems, on budget spreadsheets and administration than doing science. But I am an astronomer by training. And so I thought I'd spend the bulk of the day today talking about the research project that I've been involved with at Lowell for 23 years, ever since I came there in 1992. It's a program that is uniquely suited to the kind of thing we're really good at, which are projects that take a long time to unfold and that require a lot of observing time. Since we own all of our own facilities, we're uniquely set up to do these kinds of things, to look for patterns in nature that don't unfold on the timescale of, say, a 3-year grant cycle. But you need a little more time to uncover what's going on. So we'll go ahead and talk about the variations of the sun and stars like the sun and how that all connects to the topic of climate change. Now, I was born and raised on the East Coast, did all my schooling back there, didn't move to Arizona until I was 27. And one of the joys of living in the Southwest are just these extraordinary vistas. If you have seen Forrest Gump or perhaps driven this road, this will look familiar. Principally, this picture is proof that I am crazy enough to stand in the middle of the road in the interest of getting an iconic picture. But this is just up north of Monument Valley, just north of the Arizona border, in an area that was inhabited back in the 1200s by a people locally referred to as the Anasazi, the old ones. There are remnants of their habitations all over this area that we call the Colorado Plateau. One of those habitations is not very far from Lowell Observatory in Flagstaff. This is only about 30 miles out of Flagstaff at Wupatki National Monument. So where Flagstaff is a a cool ponderosa pine forest, you don't have to go far out and far down to get into a rather spectacular open desert setting. This was in 2012, and it was on the day of the annular eclipse. And the Park Service invited us out to the Pueblo for a talk about eclipses. And so I went out there and gave a talk right here. This is the old community room at the Pueblo, where they would gather for whatever oral history they were recounting. And it was an incredible environment to give a talk about the universe. The park superintendent told me they had more people there that day than probably ever in history. There were about 1,500 people. And sort of to stand there and talk about eclipses in the ruins of this Pueblo, where probably 1,000 years ago, people long gone did exactly the same thing, was really, really a neat thing to do. As you can see, it's just ruins. The whole area of the Colorado Plateau was abandoned by the Anasazi between about 1270 and 1300. The archaeology books that I've looked at say that there was possibly a little bit of internecine strife and fracturing society, but the tree ring records of the time also indicate there was a protracted 30-year drought in the period that no doubt would have stressed the environment severely and quite possibly contributed to the abandonment of the area. So, given what Arizona is normally like, 3 decades of drought could be a pretty severe thing indeed. So there's an example there on timescales of decades, very near where I live now, of significant climatic changes coming and going. And so we'll just file that away and come back to it a little bit later. So 2012. Now, Flagstaff doesn't always look like this. Sometimes Flagstaff looks like this. This was 2010, which was the last really strong El Nino year. You've been hearing about El Nino lately. What it tends to do is create a higher probability of wet winters in the Southwest due to the impact on the location of the jet stream. So this was late January 2010. It was unquestionably an El Nino-linked event. We had a series of 3 storms come through that dropped about 4 feet of snow in Flagstaff, and out where our 4-meter Discovery Channel telescope is, we had about 6 feet of snow, and that was when we authorized the purchase of a Bobcat, because we just you can't plow that stuff. You have to lift it out of the way. So severe snowstorms are certainly known to strike, and not just in 2010, but there was a whole spate of them in the late 1880s. This is New York City after the Great Blizzard of 1888. Back in a time when civil services were much less equipped to deal with this kind of thing. And this was part of a series of extremely harsh winters in the 1880s that hit the United States. You'll find that recounted in the history textbooks, as well as in popular literature. The late James Missioner used this in a couple of his novels, describing the harsh conditions in the upper Midwest, where trees were literally exploding as they froze in the night. And massive cattle die-offs and so forth. So this was another period, the 1880s, of unusually cold, severe winters in the United States. Going back into time a little farther, this is Louis XIV, one of the longest reigning of the French kings, 1643 to 715, sometimes called the Sun King, right? And there's a very interesting connection here. A period of about 70 years of very long, severe winters in Europe, stretching almost perfectly coincident with the reign of Louis XIV. Shortened growing seasons, heightened crop failures, famine, a very difficult time. We'll see the significance of this in just a minute. As an interesting aside, we mentioned my interest in music, which has been long-standing. There is some discussion in the literature. This was the era when the Stradivari family and the Guarneri family were building the violins that now sell for $20 to $30 million a piece. I had the privilege of hearing Rachel Barton Pine just a couple of months playing the Brahms concerto on one of the Guarneri violins that Brahms himself picked out for that concerto. It was kind of cool to hear. There's been some theorizing that the unusual climate affected the tree growth patterns in Europe at the time and created wood with a slightly different density and characteristic that leads to the extraordinary sound of those particular instruments. Just an interesting little aside. So here we have evidence shown in 3 different slides of different types of undeniable climatic shifts, all within fairly recent history. 30 years in Arizona of drought, a decade of severe winters in the United States, now 7 decades. These unusual periods can persist for a very long time. What might be the reason here? So let's switch from climate anomalies and talk about our nearest star. And having gone back in time, now we'll come back forward through time and survey a couple of the things that we've learned about the sun and how its activity changes. So sunspots, the well-known phenomena on the surface of the sun, have been observed for millennia. There are occasional naked eye sightings of sunspots going way back into the records from the Orient, but they're very spotty because it's not really easy to observe the sun directly. 1610, which was about the time of the invention of the telescope, began the first series of really systematic observations, beginning with Galileo and his contemporaries. And one of the first things he noticed was the spots weren't always in the same place, but from day to day, they would move across the surface of the sun. And Galileo reached the brilliant intuitive notion that the spots were associated with the sun and that the sun rotates. As you may know, this got him into a whole lot of trouble with the religious authorities of the day for suggesting that not only was the sun not perfect and stationary, but it had these ugly black blemishes on it. But nevertheless, Galileo derived a rotation period for the sun remarkably close to what it actually is. He was a fairly sharp guy. So 1610, so what do you do if you are aware that sunspots exist? You count them. And people ever since 1610 have been tracking how many sunspots there are. So let's look at the evolution of that record. By 1845, a German astronomer named Heinrich Schwabe made the observation that there was a periodicity, that on the timescales of about 11 years, the number of spots would rise, fall, rise, fall. I guess I do have a pointer. Rise, fall. By 1900, you might ask, here we are, 1845, we are about 2 centuries after the first observations of Galileo. Why in the world did it take so long? I mean, this looks pretty obvious. So why did it take so long for that to come out? There are basically 2 reasons. Number one, we didn't have, I mean, this was slightly before the invention of the internet, so we didn't have quite the level of information exchange that we have today. People were keeping records in more isolated areas. But beyond that, here's 1610 and the first observations from Galileo, but then look right here. There's a period when basically there were no sunspots at all into the 17th century. So after nearly a century, if you were an observer of sunspots, you would never have the remotest idea there was any kind of cycle going on. So it was really only until up in here it really started to become obvious that there was a cyclic pattern. Now, remember Louis XIV. This is about 1645 to 1715. So this coincides precisely with the period of unusual severe weather in Europe, Siberia, the United States. And so here you have a very interesting, compelling set of circumstantial evidence for an apparent cessation of the solar cycle, creating a substantial climatic impact here on Earth. And this, by the way, is an astronomer in England named E. Walter Maunder, and his name will come back shortly. And then to complete the tour of our understanding of the sun, this is a fellow named Charles Greeley Abbott, who lived to an admirable age. He died in the 1970s at 102 or something. But he spent virtually his entire career trying to observe what he thought were not just changes in spots, but changes in the entire brightness of the sun. astronomers throughout the 20th century were interested in measuring, how much energy are we really getting from the sun? What is what we called the solar constant? Because the assumption was that the sun is constant. And if you look up at it from day to day, it certainly has that appearance. It's this nice bright light that looks pretty steady. Abbott was using the best equipment available to him of the day to try to see if the sun actually was not constant. Maybe it varies. He came to the conclusion that it was. This is an example of getting the right answer for the wrong reason. He didn't have the equipment that can detect the solar variability we know today, but he was convinced that there were solar effects on climate and that the sun varied. His work led him to tempting vacation spots like Basur, Algeria here, this is nothing if not a study in perseverance and dedication for the duration of a career. But he did conclude something that we have then been asking ourselves ever since. So let's look at what the sun, our variable star, actually looks like in different guises. So this is a white light picture of the sun. It looks reasonably featureless except for the spots. So you see these prominent spot groups. For reasons we can go into in the Q&A if you like, they tend to come in pairs. They tend to be a little bit angled, tilted like that, and they appear in both hemispheres. In between, it doesn't seem like there's much going on. But today, we have instruments with the capability of observing stars in particular areas of the spectrum. And when we look at the sun in other spectral regimes or specific spectral regimes, we get a very, very different picture. So for example, in the light of the hydrogen atom, the sun is mostly made of hydrogen. A very interesting and dynamic surface appears. You see dark areas that are associated with spots, but then these very bright areas, features hanging up in the atmosphere. There's little pillars and loops off the limb. There are these dark features running here that we call filaments, and these are these, except instead of looking across them, now we're looking down them, and so they're looking dark. So these features are all over the sun. You can see a little more clearly in the light of the calcium atom. You can definitely see the spots, but suddenly we see around the spots are all of these areas, the denser, hotter plasma that we call plage, and these are areas of increased energy and increased emission that accompany all of the sunspots. And finally, now that we're in the space age, we can send spacecraft above the atmosphere and observe the sun in wavelengths inaccessible from the ground. So the ultraviolet, the X-ray, all of that radiation that fortunately doesn't reach the ground in great quantities. And when we look in the sun in the light, say, of the iron atom, it looks very different. I'm going to show you two images of the sun in the light of iron. So this is in the far ultraviolet, 17 nanometer light. And this is taken near the minimum of the sunspot cycle. So when the sun is relatively quiescent, and you can see there are a couple of active areas. You see these beautiful like loops of material over here, but otherwise it's mottled. You know, there are clearly some striations in there, but overall fairly quiescent. However, just a couple of years later, near activity maximum, it looks like this, okay? So now you can see clearly there are active latitudes. Look at the size of that loop. On this scale, the Earth would be a little bit bigger than the laser pointer dot. It would be, but not a lot bigger. So this loop is considerably larger than the Earth. These are right here as well. If you could superimpose the white light image, you would see sunspots at the base of this loop. That's why they tend to come up in pairs. And see, there's an region. You see spots here, spots here, spots here. So this is the active sun, and you can see the sun is wildly different as it goes from its activity minimum to its maximum. So this lends some credence to the effect. I mean, what is climate? Climate is the thermal environment of Earth's atmosphere. The fundamental driver of that environment is the sun. So we have this interesting possible correlation with solar activity and climate. And finally, 1978, we began to answer the question rigorously that Abbott could not answer with his equipment. So this There's a little satellite called Nimbus 7, was launched in January of 1978, and it was the first of a series of satellites that had aboard it an instrument that simply looks at the sun and measures its total brightness, whether it's optical light, infrared, ultraviolet, the integrated brightness of the sun, how much energy is hitting Earth. The reason you want to do this from above the atmosphere, and the reason that Abbott couldn't reach the conclusion he wanted to reach, was the interference. If you go out on a night, you see twinkle, twinkle, little star, right? So astronomers hate twinkle. It might be, sort of a romantic image of a star, but what you're getting is that nice pencil beam of light from the star that has made its 60 trillion mile trek across the universe to Earth, and in the last 50 passes through Earth's atmosphere, and the turbulent motions in the atmosphere start deflecting it and refracting it, and so you get this. And if you see stars like Sirius and the big dog low in the atmosphere, and you'll see it flashing green, and that's the colors being refracted in the Earth's atmosphere, so that every now and then it almost appears to change color on you. And that was the effect that made it impossible from the ground, and even today, almost impossible to try and do those kinds of measurements. You really need to do them from above the atmosphere. This was the first satellite to do it. Since then, there's been a string of satellites that have continued that record, and they show incontrovertibly that as the solar activity cycle rises and falls, the entire sun gets brighter and fainter. So its total energy output rises as it gets more active. Actually, what I will do is back up a couple of slides and explain how that works. Let's see. Here. The basic idea is, as the sun gets more and more active, there are more spots. So there are the spots. And spots are dark. So it would seem like more activity should make it fainter. And the reason the spots look dark is that they are cooler than the surroundings, where the visible surface of the sun is only 10,000 degrees Fahrenheit or so. The spots are maybe 7,000 to 8,000. So they look darker than the surroundings. But then look around the spots. There's all this bright stuff that comes with the spots. And the going idea is there's this two-component model that as the sun gets more active, you have it get the spots darkening and all of the associated regions making it brighter, and the bright regions win. So there's an offset, but the bright regions more than offset the dark ones. So it gets brighter as it gets more active. So the fact that the solar energy changes as its activity changes led this fellow, Jack Eddy, published a wonderful paper in 1976 in which he called attention. So this was published in Science. If you Google Jack Eddy, Bing Jack Eddy, Jack Eddy Science 1976, you might find this paper. It's totally readable. It's wonderful. He calls out this period of solar quiescence and coined the term Maunder minimum after E. Walter Maunder, who was the astronomer who first noticed it. And then he presented the entire sunspot record, one of the great achievements of modern observational science. And so you can see what happened here. The cycles kind of went away. This period is very well documented. There were not many spots. Very few reports of aurorae in that time, which solar activity causes. Then it coughs back into gear, but you can see that there are lots of patterns beyond just 11 years, right? So there's this, sort of an 80 to 100 year pattern. So you let your eye trace the peaks of the cycles, right? Which we now call the Gleisberg cycle. There's even a general overall tendency for steadily increasing amplitudes of the cycles. So the sun is clearly doing things on timescales much longer than 11 years, longer than 100, and in all probability, longer than even 400 or 500. But we haven't had the window to observe them. And that's one of the real things we struggle with, I think, in doing science. As scientists, trying to be rational and objective and logical, and yet we're looking at these grand patterns with our 70, 80 year window onto the universe, or whatever we are blessed to get, and that there are things that operate on such grander timescales. You might notice some interesting things in here we can discuss a little bit at the end. Right here, if you may have read about the year without a summer, it was right here. Now, in this case, actually, it was probably a volcano. It was probably a volcanic eruption, not the sun. Here's the 1880s. That's probably more volcanoes, okay? So we'll get back to that. But there are reasons for things to change other than the sun. But nevertheless, these interesting correlations remain. Here are the modern solar cycles. So this is the sunspot number from 1960 up to about the present. And one thing you will notice is here's a strong cycle, slightly weaker one in the 70s, stronger, stronger, and now weaker. And now the current cycle that started in 2010 is one of the weakest on record. It's actually a very sedate cycle. And there have been studies published in the literature starting in about 2006 that predict that the next cycle might be almost non-existent. Now, there's interesting evidence that we may be transitioning out of a period of strong cycles and back into possibly even another grand minimum akin to the one of 400 years ago. If that were to happen, it would be extremely interesting. You know, we learn a lot from nature when it does something unusual, because it lets us kind of explore the boundaries of the parameter space. So to see another solar minimum would be very interesting to observe. We have to be extremely careful with this kind of science, however. As we've learned, there's a really compelling correlation between the Maunder minimum and climate, and possibly between other periods of solar quiescence and climate. For example, you can trace the solar activity record back beyond 1610 and try to reconstruct the sunspot behavior. You can't do it with telescopes because they hadn't been invented, but you can do it with tree rings, and you can do it with ice cores and isotope records. And when we go back and reconstruct, one thing we find is there appears to have been another little solar shutdown between, guess when? 1270 and 1300, precisely corresponding to the Anasazi abandonment of the Colorado Plateau. Now, you wouldn't publish that as a formal claim in a scientific paper, right? It's a correlation. Well, here's a really strong correlation that persisted for about 20 years back in the second half of the 20th century. The number of sunspots, here's 2 full solar cycles going up and down. And up here, you'll see these little elephants. This is another striking correlation, okay? And there's a striking anti-correlation with the number of Democrats in the Senate. What would you imagine? So this is a slightly absurd example, but there are plenty of papers in the literature back in the early part of the 20th century comparing solar activity to things like commodities prices, which, you know, if you're talking about climate effects, maybe, but the stock market. You know, so the road to ruin is littered with the bones of a lot of people who have looked a little too hard for things that maybe weren't there. So what can we do if we want to understand? Yes, sir.
I don't know if you want to take questions or.
Oh, anytime. Yeah.
You're talking about the brightening and dimming. How much is the brightening and dimming?
I should have mentioned. Yeah, it's about a part in 1,000. So 1/10 of 1%, which was below what Abbott could have measured. Yes.
You mentioned 1270 to 1300. Is that the Little Ice Age?
Yeah. Okay. So let's just talk about that for a bit. So the Little Ice Age is a climatic period that goes from about 1300 to about 1700. It was a period of generally cooler weather, not globally, right? It's spatially complicated, and there were severe episodes and, you know, lulls. And some of the severe episodes appear to be associated with some of these cessations in solar behavior. So the severe winters of the Maunder minimum were sort of one of the severest and last episodes. And after the end of the Maunder minimum, we seem to be coming out of what was called the LIA. Yeah.
And just to let the people online know
Oh, yeah.
that they can post an online question.
Absolutely, yeah.
And repeat that over the mic so they can.
Right, so we're broadcasting to millions here, right? Yeah.
But to let them know that they can use the interactive tool to pose a question to.
Okay, so the point there is the listeners online can post an interactive question at any time, and we'll be happy to answer that as well. Okay, so the problem, if we want to understand the behavior of the sun, and one of the fundamental questions that's been asked when we try to understand modern climate is, what was the sun like during the Maunder minimum? If the sun gets brighter and fainter as the activity rises and falls, what if the activity shuts off for 70 years? What happens? Does it sort of just start dimming, and the solar energy hitting Earth goes way down, and possibly explain a cooling of climate in certain areas? What is the sun like? What was its brightness behavior like? The problem is we didn't have a whole lot of satellites in orbit in 1645. So there's not much you can do. Or is there? So every night there's this beautiful laboratory that goes by overhead. And you've got lots and lots of stars. Many of them are very dissimilar to the sun, like the stars in Orion. You would not want to put any of those down where the sun is, or we would be crisped rather rapidly. But there are lots of humble little stars up there that are fairly similar to the sun. So since about 1960, there have been two very long-running programs. One's ours, one is another one at Mount Wilson Observatory, that were set up to observe the behavior of a whole ensemble of the stars, to use them as test particles for what the sun might be like on long time scales. The analogy I like to use when I go to elementary school classes is, suppose your teacher asks you to write a report about people, and you don't know anything about it, but you try to write a report by observing one person. If you just observe one person, you're going to have a really skewed view. You want people of both genders, all ages, all races. You want to understand people. And so using the stars, we can try to get a much more informed picture on our own sun. So this has been going on for about 50 years now at Mount Wilson Observatory using the 100-inch telescope, and two telescopes at Lowell, one of our rather older ones, a somewhat newer one. This is the one I've been using forever. So these are telescopes set up, as we'll see in a minute, to observe the activity cycles, like the sunspot cycles. The question in 1960 was, we didn't even know, do other stars have cycles, or is the sun just a complete weirdo? It was possible it might be. And then these telescopes are robots. They're completely robotic. You program them at the start of the night. They just observe all night and then email you the data. It's wonderful because you don't have to pull an all-nighter to get the data. So these observe the brightness changes. So what we've been trying to do all these decades is measure the spot cycles, measure the brightness changes, and see what they do. So here's a brief history of these programs. This is Mount Wilson Observatory, the pristine dark skies of Los Angeles, California. And this was a program initiated by a gentleman named Olin Wilson, purely coincidental relative to the name of the observatory. In 1966, he set up an instrument and started observing a set of about 100 stars, just over and over again, night after night, month after month, year after year, using the 100-inch telescope. The reason he could do this is because Mount Wilson is an institution very much like Lowell. It owns all of its own telescopes. It's not a competitive peer review process to get a one-week slice of time on the instrument, which is, say, like Kitt Peak, some of the competitive facilities work. Even if your proposal was successful, you couldn't do this kind of project because you can't get the telescope time. So Wilson patiently observed for about 12 years and found three overarching types of behavior in the stars. And you can see the inventive, romantic names that we give to our stars. HD 1835 is a fairly young star, and it varies a lot, but there's nothing really identifiable there. These are the irregular ones. HD 81809, look here. Here's a nice, well-identified up and down. About 2/3.
About 10 years?
Yeah, this is 67 to 78, roughly. Sorry, my axes are pretty small. And then about 15% of them, look here, absolutely flat. And so the question is, is this a modern day analog of the Maunder minimum? And if so, can we now observe stars like this and transfer the results to what the sun does? So the fundamental question that Wilson was able to answer is, yes, stars have activity cycles just like the sun. And yes, some stars appear not to have any activity cycles for a long time. So we kind of see the ensemble of two behaviors that we see in the sun. And then this turns out to be a very young star. And so the younger the star is, the more erratic it is. Stars are really like people, I think, in that regard, right? They sort of, as they get older, you kind of slow down. Our program is a complement to the Mount Wilson program, which is no longer running. It was ceased in 2003. This is the 42-inch telescope. Before I switched from scientist to administrator, I spent many a night out there from dusk to dawn. We have, this is a 42-inch telescope, meaning the mirror is about 1.1 meters in diameter. And we do essentially the same thing that Wilson did, except where Wilson observed a very broad swath of stars of different types, different characteristics. We have really focused our program very tightly on the most solar-like stars we can possibly find. We want to observe suns, because you don't have to get very different from the sun to have a totally different kind of star. Our program differs from the Mount Wilson program in that this is Lowell Observatory's smallest telescope. This is our solar telescope. It's a fiber optic that points at the sun, sees it as an unresolved disk. So we can pipe starlight into our spectrograph, our instrument, from the telescope through a fiber, and sunlight through this fiber, and observe the stars and the sun with exactly the same instrument. That's not a trivial thing to do, because the sun is many billions of times brighter, apparently, than the stars. And so if you try to observe the sun with your telescope, you'll rapidly melt everything downstream. So this is a way of skinning that cat. There are some of the major research observatories on Hawaii. I was giving a talk at one of the astronomical conferences, and they had their results. They were bragging about their results, that they had published 40 papers per square meter of aperture. And I couldn't resist pointing out, we have published many trillions of papers per square meter of aperture. I think some people thought that was funnier than others, actually. So what do? The problem with observing activity cycles of the stars is we can't take a picture of a star and see a spot. They're too far away. So all of the stars, or nearly all of them, are point sources. So we can't take an image, we can't count spots like we do on the sun. So imaging is out of the question. What we can do is take their spectrum, which is like the star's fingerprint. So when you look at the spectrum of a star, you'll see that it is shot through with all of these dark lines, the absorption lines, and each one of those lines is caused by a particular element in a particular atomic state. So these two really dark ones are caused by calcium, and you'll recognize there's the calcium image of the sun. Okay, and then this one, so that's the sun. This is the spectrum of the sun here. This one down here is a star that's a little bit cooler and fainter than the sun, and it's got lots and lots of lines, and the calcium lines are not as distinct. There's tons of iron lines in here. And then finally, one of the hottest stars we observe, this is Altair in Aquila the Eagle. I've just done a graphic there putting it relatively to scale to show you how big it would probably be compared to the sun, and that's what its spectrum looks like. The takeaway here, every spectrum is a little bit different. It's literally like a fingerprint. And with the spectrum, you can tell how fast the star is rotating, if it's moving towards you or away from you through the Doppler shift of the spectral lines, its composition through the strength of relative lines caused by different elements, and finally, these calcium lines, since the star gets brighter as it gets more active, at the bottom of these calcium lines you see little spikes of bright emission, and you measure those. And as the star gets more active, that goes up, and then it goes down. So you can create these plots that are proxies for spots, flares, and activity in the stars. You can graph out stellar activity cycles using the spectrum, even though the star itself is just a dot. So there's our instrument. This is slightly a vintage instrument as of this point. It dates to about 1990. But I'll just show you the basic optical train and how these things work. The fiber comes in here, and the first thing the light hits is a beam splitter, and it goes in here, and right there you can see a diffraction grating, and this is where the calcium light gets into the camera. And that diffraction grating is using kind of the same principle as if you hold a compact disc very obliquely and you see colors coming off the surface. Then on this side is another type of dispersing system that collects a different part of the spectrum. So we get a large swath of spectral lines. There's the grating, and then there's the mother of all prisms right in here that splits up the light and it's putting it on our detectors. The detectors we use are the detectors of choice in astronomy today, which are CCDs. So exactly what you got in your phone. And they were just coming into use in astronomy when I got into the field in the early 90s and revolutionized how astronomy's done. Yeah.
You need both a grating and a prism for the same spectrum.
Yes, yeah, that's really an excellent question. The reason for that is we want to observe the stars at pretty high resolution. This is a special type of grating called an Echelle, and so it gives you high resolution, but as a result of that, a lot of the orders of diffraction get stacked on top of one another, and so the prism is a cross disperser, and it's actually really beautiful, right, for a CCD, because you have all these stacked orders in the cross disperser and you get this rectangle of orders, so you get the whole thing on one little chip. So I'll give you just a couple of case studies here. This is the star 18 Scorpii, and all I'm showing you here is a plot of its activity. So this is the light going up and down in those calcium lines. This star is a fairly modest little fellow. If you go out and look at Scorpius in the summer, you could just barely see it at the edge of naked eye vision. It's a dead ringer for the sun, as close as we can find. It's got a cycle that's maybe 7 years long, so considerably shorter than the sun's. So there's an example of a star very similar to the sun, but with markedly different characteristics, at least as far as the length of its activity cycle goes. Here's a young one, Epsilon Eridani, which has a planet around it, by the way. Very fast, 3-year cycle. Here's one that's almost close to a Rosetta Stone of what we're looking for. And I really wish we had a few more years of data on it. Look here, nothing going on, and then it starts going into a pretty vigorous 4-year cycle. But there's nothing there. So, question, is this an example of a star that did what the sun did 400 years ago? It wasn't cycling and then what it was. To be really confident of it, I would really like to have 3 or 4 more years of a flat tail to demonstrate. But otherwise, it really looks like it did what the sun did in 1715, because if you see, the cycles are gradually, it's like it's coming out and getting itself ramped back up. Yeah?
Is your hope that your cycle will be faster with a star that only cycles every 4 years versus 11?
Well, that certainly helps not having to wait 11 years to confirm that it's actually a cycle. So the length of the cycle may have to do with the rotation rate of the star. There's a lot of relationships between how fast the star is rotating and the characteristics of the activity in the cycle, because rotation is one of the things that generates it. And then if you take our program in Mount Wilson's, I just love long series like this. Here's the combined series of 2 stars that we both observed. And we pick out things that would be impossible to get on a short program. So here's a star that has a primary cycle that we pick back up. And so we'll be expecting another one out here that's about 17 years, but then superimposed is this really fast 2-year one. And then it kind of settles down. There's a little gap where Mount Wilson wasn't observing it. It comes back up, and it settles down, and it starts back up. So you see the same behavior getting recovered. There's actually a little bit of something like this going on in the sun. There's the 11-year cycle, and then there's a little lower amplitude 2-year thing. So putting all of this together, where do we end up here? So So we can ask a couple of questions. From what we've been able to observe so far, as we observe the activity of the stars, and then we observe their brightness. So do stars get significantly fainter when the cycle turns off? What might be the climatic implications of the cycle turning off? Well, here's where science gets really, this is why I like working in science, okay? So these are plots of the stars from the Mount Wilson program and from ours. And Mount Wilson, the Mount Wilson data suggested those are cycling stars and those are non-cycling stars. So when a star turns off its cycle, it slides into a really low state of activity, and thereby you infer it might become significantly fainter. If a star becomes significantly fainter, then there are implications for how much solar forcing you might plug into climate change models since the 1700s. We couldn't recover the result. So we are using stars much more like the sun, and we were using about close to 60 stars in this study, about 57, and this is based on 13. So you've got statistical weight coming in, and here the blue, these are our cycling stars, the red were our non-cycling stars, and the yellow is the sun. So we've got the sun as well, and we couldn't find any statistical difference in the samples. So our initial conclusion was that the Maunder minimum sun was probably like the modern sun, except without the cycle, and it wasn't really sinking into a very, very deep minimum, granting that there were significant effects on climate. But at least from what we have now, we think when the cycle seems to turn off, it's sort of just ceasing and not really changing its basal magnetic state until it gets going again. Okay, does the sun affect climate? Yeah.
I'm sorry, on the previous graph, so you said the red is the stars that were not cycling.
Right.
Those are the stars that you saw cycle, and then this is the measurement of the flat, or these are ones you never saw them cycle?
Right. Those are kind of the flat ones. We've got that one star where we think we may have seen a transition, but that's only one. So what we really need to observe are more transitions. But this is the set of stars where we look at them, and it's like if you looked at the Maunder minimum and you happen to catch that section of it, just like that.
But you don't know whether when it goes from cycling to flat, maybe it's different from stars that are just always flat.
Maybe it is. That's right. And that's going to be in next steps here at the end. Yeah. Does the sun affect climate? It does. So this is from a paper I think published around 2001-2, just to demonstrate the differences in global temperature between a solar maximum and a solar minimum. So measure the temperature of the Earth at spatially resolved at solar max, solar min, and color code it. So the red areas are warmer, the blue areas are a little bit colder. So a solar max is a little bit warmer out here, a little bit warmer in Seattle. Western US, Eastern US tends to be a little bit colder. We're talking 1/10 of a degree here. You know, it's not profound, but it's measurable, right? You can see it. And so it does, and here there's pretty significant effects in Siberia. So even though the overall variation is pretty small, if that were to cease for not, a year before rising up, but for 70 years, you can imagine that there could be significant climatic effects. Since 1700, we think of climate change or global warming as kind of a modern day problem or issue. Earth has actually been warming since the end of the Maunder minimum in 1700. And here's how that kind of stacks up. This is from another paper published in the early 2000s. So here's the 400-year sunspot record again. And then here was the best conclusion from the folks who try to do the climate reconstruction. So to do a climate reconstruction, you look at all the variables, you plug in the changes in the atmosphere, the circulation patterns in the atmosphere. You use solar forcing, right? So how much has the sun changed over the last 400 years? And that's kind of where we plug in. I'm not a climatologist, but from an astronomical side, we're trying to say, okay, well, the stars indicate the sun has maybe changed this much since it came out of a grand minimum, not this much. And so when you do that, you can put together an irradiance reconstruction for the solar brightness. And the conclusion here was that after 1700, this solid dark line is temperature right here. So slowly rising after the 1700s, then there's a little down, then it starts coming up, and then if you continued this, it would continue on up to about here. So it's going up rapidly at this point. And then the reconstructed solar brightness tracking it reasonably well until very recently. So mostly solar forcing. Solar activity does influence climate and it does influence global temperatures, albeit in a spatially complicated way. Then notice right here, mostly volcanic forcing. So in the 19th century, there were some very large volcanic eruptions. Tambora in the early 1800s, Krakatoa in the 1880s, right in that period of severe winters. You can see a brief dip in the record in 1991 after Pinatubo went off. And what's going on there is volcanoes are throwing large clouds of aerosols into the upper atmosphere, which tend to lower the temperature because they reflect sunlight. But the difference between aerosols and, say, carbon dioxide is aerosols precipitate out quickly, whereas carbon dioxide and methane and other greenhouse gases stick around for a long time. Evidence from the 20th century and particularly the last 40 years, the generally strengthening solar cycles up to the 1970s probably contributed to some of it, but the best guidance is 25 to 30% of modern warming in the last 4 decades or so can be attributed to solar forcing. The rest of it must be due to anthropogenic or man-made effects. So that's kind of the suite of things since the end of the Maunder minimum. And the stellar guidance from the long-term observing programs is that recently the sun is not the principal contributor. So now where are we going from here? Well, it's a very interesting time, as I alluded before. We had the long Maunder minimum. This has come to be called the Dalton minimum. So it was a period of some really weak cycles, and then it came back up. We had a period of very strong cycles in the 20th century, and now it's really settling down. And people are hypothesizing that we might be heading into another period like this one. Is that going to happen for sure? I do not know. But the people who are arguing this are measuring the strength of the sun's magnetic fields right around the sunspots and finding that they're rather weak, and using that to project a very low sunspot cycle, a sunspot number for the next solar cycle. So I think everybody kind of poo-pooed this idea when it was first floated in 2006, but there's been increasing acceptance of the idea that we might be transitioning into another period of solar quiescence. One other thing sort of arguing in favor of this is the folks who look at solar activity on really long time scales have done some analyses of, when there's a period of strong cycles, how long do they usually last? And you base that on the ice core records and the isotope records. It seems to be typically about 80 to 100 years before the things change. And this is, kind of where we are. If the current set of strong cycles started around 1920, we are coming up to that. So it's an interesting time to be in the field. And the thing to do now is, coming back to a question from before, we need to observe transitions. We need to observe stars that are really like the sun. And the problem is, once you narrow down the parameter space that much, you don't have a big sample left. So you have to go to fainter stars. And we can't go to fainter stars because they take too long to observe. So we need a bigger, like Roy Scheider in JAWS, right? You're going to need a bigger telescope. And so there's yours truly here. These are some folks from Northern Arizona University. And this is Lowell's new telescope. It's called the Discovery Channel Telescope. So you may be able to infer where we got a capital gift to help fund it. Otherwise, was entirely built with private funds. It has opened up a tremendous new era of opportunity, but for Lowell. But one of the things we can do with this is reach much fainter stars than we have before. So now what we want to do is go from the studies I've been talking about today to more focused studies of the small-scale magnetic fields on stars that are not cycling, and try and understand how they are different from the cycling ones to provide some guidance on what might happen in the future, so that should the sun actually go into a minimum. So stay tuned. Before the sun makes any of us any sort of latter-day Anasazi, we'd like to understand what's going on in the future, and it's been a really interesting project to be part of, and we'll keep you posted. So that's getting close to an hour, and I definitely want to leave time for a little bit of Q&A if we have time for some.
Sure.
Okay, all right, so I'll stop there and happy to take any questions. Thanks very much. Yeah.
Are the ice ages, can you do any correlation with the ice ages like the from 10,000 years ago?
Yeah, this is what I always like to point out in a talk like this, is that we are living in an ice age. Yeah, so we happen to be in an interglacial, but there's freestanding ice on the Earth's poles. So now we're talking about phenomena that play out over 40,000, 100, long time scales, and have been linked to slow changes in the Earth's orbit, the so-called Milankovitch cycles. So these are effects that are playing out on somewhat faster time scales than the ice ages. So during the dinosaurs, the era of the dinosaurs, which was not an ice age, you had all of the continents kind of gathered in one big blob, and oceans circulating around the poles. Now we're in a phase where you've got Antarctica, a landmass sitting at the South Pole, which allows a large amount of freestanding ice to collect. And the Arctic Ocean is kind of hemmed off by North America and Asia. So we're kind of in a configuration now where an ice age can exist. I think Earth has only been in an ice age for a smallish fraction of its existence. And right now, within an ice age, so there are advances and retreats, and we're kind of in a retreat right now.
Correlate at all with the sunspot cycles or anything?
No. Yeah. I mean, first we can't quite.
How would you know?
Yeah, we can't trace it that way. Yeah.
Could you say a word about Carrington events? How they correlate with sunspots and so on.
Well, so that's a function of the solar activity cycle, but I mean, it's not directly tied with like climate connections.
But do they appear at the peaks of activity? Do they get stronger? Are they?
Not necessarily, no. So there's more activity, more violent, more eruptive events in the sun's atmosphere at an activity maximum for sure. Yeah.
Do we know why sunspots are even?
Why they happen?
Why they even happen, and why is there even a cycle?
We know the basics of that, yeah. So the cycle is a combination of the sun's rotation, so it's tied to the rotation, and the turbulent motion of the convective material below the sun's surface. Since the magnetic field is a property of the matter in the sun, as the sun rotates, the magnetic field kind of gets twisted up. The sun is not a solid body. So the equator rotates roughly once every 25 days, the pole once every 33 days. And so as it rotates, there's this twisting of the magnetic field that's then given a torsional component by the convective motion. And that produces what is effectively a magnetic dynamo. And that's what's producing some of these loop-like features you see. And so the solar cycle is the gradual ramping up as that geometry gets steadily more complex, followed by a settling down as the active regions reconnect and diffuse and are recycled into the solar interior. So the bulk nature of the cycle is well understood. The full calculation has been beyond the reach of even modern computers, and the full details are not understood, let alone why it would appear to cease. And one thing we can tell, when the sunspots disappeared for 70 years, there is still ample evidence in the isotope record that the variations were going on. The dynamo was still operating, but it was just at a much reduced level, at least macroscopically. So something was still going on and continues, but we don't understand what would cause it to settle down and then ramp back into gear. There was another question somewhere, yeah.
So how did you decide on the list of sun-like stars that you're going to observe?
Yeah, so we're limited by the size of our telescope to stars of a certain magnitude. So we go down to about 8th visual magnitude, which is maybe 60 times or so fainter than you can see with the unaided eye. So what you do is you use stars that are measured to have properties as near as possible to the sun. So every star has what we call a color, which is sort of the difference in brightness in two different parts of the spectrum. So you look for stars that have exactly the same color. They might be chemically similar, as you can determine from the spectrum, have similar rotation rate, to the extent you can determine a star's mass, which is very difficult to do. So you just look for the nearest stars to the sun within that parameter space. They're just not that many. You know, when you're limited to really bright stars by your instrumentation, you're limited down to a pretty small sample. By going to a much bigger aperture, then we suddenly have a much larger sample to pick from. And we've got lots of stars that are known to have planets, and those would be really interesting to observe.
What percentage of stars would that be?
Well,
Down to magnitude 8.
Well, down to magnitude 8, 9. Well, so there are some stars that have been identified at 8 and 9 that are even better than the one in Scorpius as dead ringers for the sun. So a handful of them. If we could get to magnitude 11, you'd have many tens probably. So you'd have a much better sample to kind of pick and choose from. And then what you would want to do is design an observational program that would get you some more understanding quickly, because you don't want to spend another 50 years, or 70. I'll be sick of this project by the time I'm 130. So we want to, find a way to infer what's going on a little more quickly than just sitting around for 70 years and saying, okay, that's really not cycling. Okay, it's still not cycling. Yeah.
Are there any data mining opportunities from projects like Gaia that are doing, many different observations, albeit they're doing it for astrometry, but they're also getting some photometric data?
There are, yeah, absolutely. And so, say from Kepler, you can definitely use the Kepler observations. In fact, I've got a collaborator down in Tucson, and we've got a little project going, or will have a project going next year, to observe some of the Kepler stars. Yeah, for sure. And then, like from the Kepler data, you also can identify, you know which stars have planet candidates, and a number of those are quite sun-like. So you can go start hitting them. The problem is we can't do those stars with our current facility because they're too faint. But I've got, if we can get a spectrograph that covers the right spectral features, I think we can go to those stars and make some observations that would get some interesting results pretty quickly on how they differ. Because you can use a really neat inference, right? You could observe the current stars. We've got stars that we know are cycling and stars that we know don't. So observe them in this new way and see what they're doing, and then observe some of the fainter ones and infer from, okay, these do this if they're cycling and not. So maybe these are doing this, and infer which ones are actually in a quiet state. And then you don't have to observe them for like 10, 12, 15 years.
When I was at your observatory,
What?
I took a visit there, and upon entry there was this little dinky telescope that they were showing the sun off with. And now I had a chance to look through that, and it's amazing.
Yeah.
And it was like a sort of a slinky sort of effect as the sun went across itself. Could you explain to us maybe what that is? Like it kind of looked like you could watch the sun. It looked like a wave kind of rolling across the front of it.
That might just have been turbulence in the atmosphere. Yeah. So what you were probably using there, it looked orange, right?
Yeah, it was a little tiny scope. It was
just like this.
Coronado or something?
Coronado, yeah. So that's a solar telescope, and it's equipped with a hydrogen alpha filter. And so that's exactly what I was showing you before, the hydrogen image of the sun. And so often what you see there, you'll see motion, and that's kind of like seeing twinkle. Because you're seeing turbulence in the atmosphere that's creating this apparent motion on the surface of the sun. Sometimes you actually see features evolving. You can see a flare, and 15 or 20 minutes, it'll be different because they really do evolve on that kind of time scale. Yeah?
How do you calibrate long-term brightness measurements?
Oh, okay. So that's good question. So those photometric telescopes that are observing the brightness of these stars, we observe them in quartets. And so you observe a program star and then 3 stars that you kind of select for being completely dead, so their brightness isn't varying, and you do a differential between them rather than an absolute, because that's really hard to do. And so what we typically do is we'll observe 4 of them and look at the differences between all of them, right? And then pick the 2 that are the flattest, and then we'll reference the program stars to those. But what will happen every now and then is one of your program stars will go on, and suddenly it decides, it's like, oh man, if you want to make a star variable, just pick it as a comp star, and then that'll guarantee it'll start doing something weird. So it's all differential photometry. It can actually be done very, very accurately. We have to get down to about millimagnitude to make that work.
I have
A great
online question.
Oh, all right.
What is the approximate max distance from our solar system of these 8th magnitude sun-like stars, e.g. 100 parsecs, 1,000 parsecs?
Okay, very good question. So the sun, if it were 10 parsecs away, it would be about 5th magnitude. So the stars we're looking at, like 18 Scorpii, is, I think it's like 40 parsecs. So we're going up to 50, 60 parsecs away when we're doing a star with solar luminosity. So that is 180 to 200 light years, which in the grand scale of the cosmos, we aren't even getting off our front porch. So these are nearby stars. If we start doing the stars that Kepler is looking at, then you're starting to get a little farther out. You're getting 500, 600, 800 light years. But still, that's just the local part of the galaxy. The galaxy is a big place. Yeah?
Do the number of planets, the size of the planets, their orbital distances, do they impact solar or stellar dynamics?
Great question, yeah. The answer is yes. We have observed some stars where there are planets so close to them that the planet's magnetic field is interacting with the magnetic field of the star. That doesn't happen with our sun because the planets are more spread out. But when we first started finding exoplanets, astronomy will always surprise you. And the first exoplanet we found was totally not expected, which is one of these hot Jupiters, a Jupiter-like planet, but really close to its star. The prevailing wisdom was solar systems would kind of look like ours, right? With the small, dense, rocky ones having kind of formed nearer in, and the big light gas bags formed farther out. But here was a totally different thing. And now we have found some of these stars that, in fact, do interact with the magnetic field and vice versa. So yeah. These are planets that have orbital periods of 3 days or something. So, yeah.
Does the amount of fusion that goes on in a star stay pretty steady?
Reasonably steady for a healthy star like the sun. So the sun is fusing something like 600 million tons of hydrogen to helium in its core per second. As the sun ages on the main sequence, it will gradually become more luminous. As it gets old and starts fusing other elements in its core, then things start to become increasingly unstable and the time scales become increasingly short. But the overall energy output of the sun is quite stable. And so as long as its mass isn't changing that much, you're going to have a relatively well-defined rate of fusion. Yeah.
So you said from the spectrum you can tell how quickly a star is rotating. How does that work?
Because you can tell that if there's a spectral line and the star's rotating, then this part of the star is coming towards you, and that part of the spectral line gets blue shifted a little bit, and this part of the star is going away. So as the star rotates more rapidly, the line gets broader. And you measure the broadening. There will be a natural thickness to the line, sort of if the star is not rotating at all, and then you can measure the broadening. And so that really actually gets to be a mess. If you have a very rapidly rotating star, the lines are all thick and kind of blurred together, and it can actually be pretty difficult to determine what the rotation rate is. Okay. Anything else?
Well, let's...
All right, thank you. Yeah.
Thank the speakers.